Okay, let's start with the linear quad element. Now, quick summary is that the reference element, remember we are using the reference elements because the Gaussian quadratures are defined. I mean, it's very convenient for the integration to use Gaussian quadratures, so it's much easier and much more convenient to use the reference elements to derive all the matrices. So the reference element extends from -1 to 1, both in psi and eta. The local numbering of nodes always goes in this direction. It's like first local node, second, third, and fourth local node. Well, and what kind of shape functions do you have? Can anyone guess? It's time for me to drink tea. What do we need to have? We need to have a shape function for the first node that is exactly 1 here and is 0 everywhere else. And we want to have a linear element. Actually, it's not really linear, it's bilinear. So let's take something like that. 1 minus psi looks like something that will give non-zero here, and it will give 0 here. It's already pretty good. Let's do the same. Sorry. 1 minus psi obviously gives 1, something that is non-zero here, and what is 0 here. And let's do it in the other direction. 1 minus eta repeats the same process in the other direction. Well, but the bad news is that it's 2, 2, so we need to divide it by 4. Then it's easy to write the second function because it will be, we just need to flip the sign here, just reverse that. And, well, again, nothing changes in the eta direction. Phi 3 is, okay, we are not changing anything for psi, but right now we need to do something different with the eta direction, and phi 4 is 1 divided by 4. Well, 1 minus psi, because again it needs to give something non-zero for negative psi, and 1 plus eta. Good. Linear triangular element. Here, the definition, the geometrical definition is a bit different. As we've mentioned, it extends from 0 to 1 and to 1 in both coordinates. The local node numbering is also same, like first, second, third local node. So what is phi 1? Right now they will be really linear. 1 minus psi minus eta. Phi 2 is nothing else like just psi. Phi 3 is simply eta. Short comment, well, this element is really linear. This one is called linear or bilinear, since you do have the product of 2 terms that are linear, each of them. So clearly such a function is not linear, but it's linear with respect to each of the free variables. Now, an extension. How do you develop higher order elements? How do you? Yeah. Why do you add mid nodes?
So you have more points for the function.
Literally speaking, I would say you do the reverse order. Like you want to add more functions, more shape functions, and more test functions, because you need to have higher order functions within each element. Yeah, but in defined element method, you do it by associating your additional functions with additional nodes. So to develop higher order element, we are additionally adding functions, shape functions that are associated with additional nodes. Now, be aware that if you take the higher order function, higher order triangular element, these shape functions do not hold anymore, because you need to derive new functions that will be like 1 here, but 0, 0, 0, 0, 0 everywhere else. And now, something that Konrad wanted me to show is how do you basically come up with the shape functions or test functions that you are using. The idea is the following, that, okay, you know that we don't want to have a linear element anymore. Right now, we are interested in having a second order element. So what would we add? We would additionally add xi squared, xi times eta, and eta squared. These are all the combinations that you can come up with if you want to extend the functions to the second order. So the general form of your shape function, shape or test function for second order is, some constant plus b times xi plus c times eta plus d times xi squared plus e times xi times eta. This one is obviously not an exponent. It's not like an Euler number. Plus f times eta squared. Good, and obviously we don't know what these coefficients are, and these coefficients need to be selected in such a way that phi 1 is exactly 1 at the first node and is 0 at each other node. Right? So what you come up with is, if we write something like that, that we've got ith function where I goes from 1 to 6. So basically, each function associated with each node at psi I, let me call it vector psi, meaning that it's like a pair of psi and eta. Psi I would be then, what is psi here and eta here, like 0, 0, then half, 0, etc., etc., like coordinates of a particular local node. What should it give? Sorry. Do you know this sign, the Kronecker delta? It's like it's 1 if the indices coincide, it's 0 otherwise. So what you require is you are using this formula with 6 unknown coefficients A, B, C, up to F. And what you can generate is you can use this to generate, you can generate 6 linear equations for the first function. Okay, how do you develop the first shape function? Well, you say, okay, I is equal to 1. And now what are my requirements? My requirements are that if j is also 1, which means that I can substitute particular coordinates of the first local node, then this formula with 6 unknown coefficients needs to give me 1. If I substitute the coordinates of that node, then it needs to give me 0. Of that node needs to give me 0, etc., etc. So you've got, well, not by chance, you have got 6 nodes, so you can write 6 linear equations, and you've got 6 unknown coefficients. You solve the system of linear equations 6 by 6, and you come up with A, B, C, D, E, and F that define the second order shape function associated with that node. Then you need to repeat the procedure to generate the formula for this one. And like I will not write it here by guessing. I probably did it 2 times in my life to generate this formula, and then you're simply using them in the code. Yeah.
Are there cases where we have to use third-order measures?
Mm-hmm. You can use 10th order elements.
Yeah, but I guess we can, but when do we have to?
I mean, if you are using higher order methods, you have less and less diffusion in the scheme. So, for example, in the scientific research, the higher order methods are, I don't want to say they are extensively or commonly used to simulate turbulent flows or large eddy simulations. But I would say one of the applications is having higher order methods to solve turbulent flows where you do not add additional numerical diffusion to the physical diffusion, and you want to resolve the vortices. So it's one of the applications, but you know there is large discussion whether it makes so much sense to go to really high order.
Are higher order methods feasible for complex geometries? Industrial geometries?
I think depends.
I think there's a problem with generation of that much.
There is.
If you've got with increasing order, you have to have like fewer and fewer elements, and if they are geometrically linear, they are not able to represent geometry.
There are two problems, and I have investigated it once with a very simple example. Like if you want to solve even the potential flow over the airfoil, if you've got potential flow, this means that you write the Laplacian of the velocity potential. So you basically are solving a diffusion equation. And we did something like that. Okay, you can use first order, second order, 8th order, 10th order finite elements to solve that flow and calculate the pressure above the airfoil. We've been doing that assuming that we either have got linear representation of the geometry or high order representation of the geometry. And it turned out that if you use just linear representation of your geometry, obviously with higher order, you've got less and less elements. And like I think the conclusion was that if you've got linear geometry representation, then second order is the best solution. Like you still gain some accuracy because you've got a high order scheme, but if you go to third, fourth order, etc., your accuracy already decreases if you keep the overall number of unknowns in the system constant. So that's one of the problems. Obviously, you can extend to nonlinear representation of the geometry, and then it's fine. The problem is that even for higher order methods, the local matrices become larger and larger, like the local matrices of the higher order element. Then your global matrix becomes more dense, not so sparse. So they're like really trade-offs.
One more question.
Yeah.
What's the difference between like higher order finite element method and spectral methods? Are they the same, or there is like?
Well, I would say finally it's the same. It's like you construct the matrices and the shape functions a bit smarter using the Cartesian product of the one-dimensional functions, because it would be extremely difficult to come up with such formula for 121 local nodes that you've got in 2D for the 10th order spectral element.
Okay.
Okay. Any more questions? Yeah.
Yeah, one weird question. Have you ever tried use linear triangle with maybe high order polynomials as shape functions? So basically 3 nodes in a triangle, but functions that we are using are high order polynomials.
High order means like second, fourth?
Maybe 10th.
Yes, I have been.
So with 3 points, we can probably generate 3 shape functions with probably 1 x to the 10th and y to the 10th. We can probably solve this equation for that, and we will come up with basically just 3 points and 3 shape functions, but very high polynomial. But how it behaves?
No, I haven't tried. You mean so you mean not having the full set of high order shape functions?
No, only the functions are 1, so const function, x to the, let's say, 10th, and y to the 10th, to the power of 10th.
I don't think they are proper shape functions whatsoever, because they don't fulfill the partition of unity.
But when won't we be creating proper shape functions using this formula?
Okay. I don't know if...
That will behave strangely, I think.
I don't think you can satisfy the partition of unity still. Because you certainly can require fulfilling this at the nodes, but it needs to be everywhere in the domain.
Oh, maybe yeah. Okay.
So I think you can't.
And I've got one more question. What about mixed order elements in one domain?
What do you mean mixed order?
Well, let's say that in the
one triangle of first order.
Yeah, let's say that near the wall we've got like third order elements, and in far field we've got first order elements. Yeah, like with hanging nodes, this kind of stuff.
I don't have much experience with that, so that I could tell you like what the properties of such a discretization are.
Hanging nodes even allowed in finite element?
Well, you can do that.
I believe, yeah,
Yes, you can do that. You can have even non-conformal meshes, meaning that you've got some subdomain with such a discretization, and I will draw it with some space in between, but assume it's really these 2 lines coincide and having different nodes. This can be done, and I have done that. Like you just need to derive smart way of interpolating from one mesh to the other and the other way around, because you need to assemble the global matrix, and that one is tricky to do it properly without errors.
Yeah, we are doing it in qubits, in contacts, and yeah.
You can do that.
What about overlapping meshes? So like, is it Chimera or something like that?
It's like Chimera method. I don't have a practical experience with Chimera method.
Okay.
Mapping from one set of nodes to second set of nodes. It's the same case as the Bartek throw in the top right. You're basically mapping one set of nodes to the second.
But in 3D, like, okay.
For all of you who don't know what a Chimera method is, the idea of the Chimera method is that, well, it's very often used for simulation, for example, of flows in moving domains. Like you can imagine, one of the practical examples is, imagine you've got an aircraft that is dropping a bomb.
As cluster separation, I think
it's
a better example.
Well, to be honest, with this dropping a bomb, I think it's one of the benchmarks that is really popular on the internet. But you can imagine such an application, and you need to have if you've got geometry that changes in time, the bomb that starts dropping, you need to have constantly mesh which is properly aligned to your current geometry. So if you once generate the mesh, then you would need to remesh every time step or every a couple of time steps, because you would be extending the mesh, but then you've got long elements, you need to remesh. Then you can simulate by like elastically extending the elements, but then you need to remesh again, etc., etc., and it's not very convenient. So what people have come up with is, you can imagine that you would have some background mesh, well, Cartesian or not, whatever this can be, but you've got one mesh which is constant in time, but apart from that, you're generating, and you can imagine you would have this like moving object. So you're additionally generating additional mesh that is associated with this moving particle, or part, that is rigid and constant, so to say. I mean, it translates or moves like a rigid body with this part. So you don't need to remesh anything in the proximity of this part. But the only thing you need to do is, you've got two different meshes. One mesh here close to your solid, and the other background mesh. So to assemble all the equations, you need to map the values from one mesh to the other, because this red one is moving with respect to the black mesh. That's the idea, but I've got no practical experience with implementing that.
I wanted to make sure that
Yep.
I understand correctly. Like when we have the second order element, the local functions stay the same even if it's second order geometry, and only the transformation becomes strange.
Once again, if you...
When we have second order geometry elements, then the local shape and functions are the same as we have just written, but...
This?
No, okay, we haven't written the second order, but yeah, but they stay the same, and only the Jacobian changes, like when solving. Like the strange triangle.
I think yes, because you are still defining them for the this
in our reference frame, they are also like
for
located the same way.
normalized
Okay, but
okay, you mean such an element.
Yeah, exactly.
Yeah, but in the reference domain, it's like a straight edged triangle.
Okay.
So yeah.